So far in this series, we've treated cells as autonomous systems managing chemistry, damage, signaling, growth, and survival under constraint. But most cells in complex organisms are not autonomous. In this final lecture of cellular biology, we ask a different question. What happens when cells give up independence entirely? Multicellular life is often presented as a simple upgrade. More cells, more structure, more capability. But multicellularity comes with a cost. That cost is autonomy. Specialization is not gain without loss. A specialized cell performs one function extremely well, but gives up many others. It loses metabolic flexibility. It loses decision-making independence. It loses the ability to survive on its own. Specialization is a trade-off, not an optimization. Once cells specialize, no single cell can function independently. Nutrients must be delivered. Waste must be removed. Signals must coordinate activity. This creates a system where individual survival matters less than system stability. Cells no longer exist for themselves. They exist for the organism. Optimist cells make decisions locally. Integrated cells cannot. Multicellular systems, cells cannot grow whenever conditions are favorable. Growth must be approved. Survival must be conditional. Behavior must be constrained. Unregulated autonomy threatens the entire system. Control is not oppression. It is the price of cooperation. In unicellular life, death is failure. In multicellular life, death can be protective. Eliminating damaged or misbehaving cells prevents propagation of error, structural collapse, coordination failure. Elimination is not a tragic exception. It is routine maintenance. Specialization and integration create new strengths. They also create new failure modes. Specialized cells are efficient, but fragile. When they fail, replacement is slow. Compensation is limited. Damage spreads. Many diseases reflect failures at points of specialization, not global cellular collapse. As autonomy decreases, signaling becomes the dominant control system. Cells must constantly know when to act, when to stop, when to sacrifice themselves. Miscommunication at this level has amplified consequences. This is why signaling failures are so disruptive in complex organisms. Once cells surrender autonomy, disease takes on a different character. Many pathologies arise not because cells are weak or broken. They arise because cooperative rules fail. Cells grow when they shouldn't. Cells survive when they should be eliminated. Signals are ignored or misinterpreted. Disease here is not rebellion. It is coordination failure. Perfect coordination is impossible. Decisions are delayed to avoid error. Trade-offs must be made under uncertainty. Failure cannot be eliminated, only managed. Multicellular systems succeed not by preventing failure, but by containing it. Once we step back, a single pattern becomes visible. In integrated systems, cells are no longer the unit of success. The system is. Cells survive conditionally. Function is negotiated. Sacrifice can be the optimal outcome. This reframes how we think about growth, damage, immunity, and disease. This is the central takeaway. Complex life is possible not because cells become freer, but because they become constrained. Once you see this, cellular biology stops looking mysterious and control stops looking optional. In this series, we've seen that complex life works because cells give up autonomy and accept control. Once that happens, a new problem appears. How does a system decide which cells to protect, which to restrain, and which to eliminate when things go wrong? That question is the starting point for immunology.